Hello friends, welcome to Truth of Physics. In our today's video, I will discuss and also solve this problem, okay? And this problem involves actually the Laplace's solution of Laplace's equation in Cartesian coordinate system, okay? By the method of separation of variables. So in this video, I am going to detailedly discuss each and every step, okay, behind the solution of this problem, okay? Now, two infinite grounded metal plates lie parallel to the xz plane. That means this plate and this plate, okay, in the xz plane, okay. This is parallel to the xz plane, okay. This is parallel, okay. Now, and these two meet the y-axis. This is the y-axis, okay. This is the origin. Suppose this is the origin. So meet at the y-axis at y equal to 0. Here this is a point, meeting point. This is the below plane, meets at y equal to 0. This is the coordinate system, and here this is a plane, okay. This is the plane which is situated at y equals to 0, this, and another is y equal to a, this plane. Now the left end at x equal to 0 is closed off with an infinite strip insulated from the two plates. That is this is like a strip, okay. This is a strip, rectangular strip. It is all over the infinite, all over to infinite, okay. This is extended to infinite, this thing. Now and which is insulated, okay, which is insulated from the two plates, this plate and from this plate. This is insulated, this strip, okay. Now and maintained at a specific potential V0. Here you can see this is V0, right? This is V0, this thing. Now what is asked then? Find the potential inside this slot. That means this is one plate, this is the another plate. There is a gap, and the distance between these two plates is a, right? This distance, this distance, this is a. And now we have to find the expression of V inside this region. What will be that? We have to solve that, right? Now how can we solve this thing? We know that the Laplace's equation. So what basically this problem actually have? This problem actually have a symmetry, and that symmetry is along the z-axis. So while let's understand it carefully, that you can see that this plate, this upper plate and the below plate, these are extended, right? These are infinite planes. That means that these are extended all over the x-axis and all over the z-axis, right? But you can see, so here what should be the potential? The potential can vary with the y-axis. Yes, obviously it will vary along the y-axis, and the potential will vary along the x-axis also, along this way also. Why? Because here the potential is V0 at this strip. So gradually you can understand that the potential will decrease in this way, right, as we move in this way. But the potential will not change along the z-axis, right? The potential will not change along this way. So that means there is a symmetry, and the symmetry is along the z-axis. Now we can so express this. We know that del square V is, and in the between in this region, where you have to find the V in this region, okay, in this region, if we apply the Poisson's equation here, then you can easily understand that the rho inside this region is 0. The rho is equals to 0. That means this will gradually become, the Poisson equation becomes a Laplace's equation here. And if we can solve this Laplace's equation, then we can find the potential, expression of potential inside. And we have some certain boundary conditions here. You can easily understand that. And what are the boundary conditions? This is number one boundary condition. This is grounded metal plate. That means upper and below plate is grounded. That means if we write V, we can express it like this: V equal to 0 at y equal to 0. v equal to 0 at y equal to a. This is for upper plate, right? Now number 3 will be v equal to v naught, this thing, right? This thing, v equal to v naught at x equal to 0. And number 4, which you have to understand, that v will tend to 0 as we move x tend to infinity, right? As the potential here is v naught y, so we can easily understand that if we move to the rightward along the x-axis infinite, then obviously this potential will gradually decrease, and one time it will, as we approach to infinity, this potential will vanish. Now from these 4 things you can easily understand that this is not depending, the potential is not depending on the z-axis. If we move along the z-axis, it is not depending on that. That means there is a symmetry. That means the Laplace's equation, this del is written like this in 3D form, del square, this del square v means del square v by del x square plus del square v by del y square plus del square v over del z square equals to 0. Now this term we can neglect this term, okay, because of the symmetry along the movement in the z axis. So this becomes a relatively simpler problem, a 2D problem, where our Laplace's equation converges to this form, del square v upon del y square equal to 0, and we have to solve this. So let us begin the solving process. We are assuming that the solution, using the separation of variable method, we assume the solution in this kind of electrostatic problem, okay, we assume the solution to be in a product form, okay. That means v of x y, the potential in between the region will be equals to x into y, okay. Why product form? Also there is another method where you can express in the, and that is also the separation of variable method, but that is additive separation of variable methods, where you choose the solution like this. But here we will not choose this type of solution for simplicity to approach to our main or actual solution. We'll use this type of solution, okay. Now we will just, as we have just assumed this, right? Now this is a function on x of x, and this is a function of y, okay. Now if we put this here in this equation, then you can easily understand that del square v upon del x square will become what? Del square v means what? X into y. So v, I can write x into y, where x is completely dependent on x, small x, and y is a function of small y only. That means this will become the x, this will be just this capital X divided by del x square, and y will be taken outside because this is what? A partial derivative. That means it will just, to it only the variable is x, not y, so it will treat y as a constant, so I will be taken outside. So this will gradually become this will become y del 2x over del x square plus x del 2y over del y square. Now if we do a thing here, divided both of these things, that is both sides LHS and RHS with xy, just divide with xy, then what happens? This x will be cancelled out, sorry, and this y's will be cancelled out, okay, and we are left with like this thing, 1 by x del 2 capital X over del x square equal to minus 1 by y del 2 capital Y over del y square, right? Now you can easily understand one thing, that x and y are complete, this is complete function of x, this is complete function of y, and x and y are independent to each other, right? If we move x from 0 to 5, then it is not sure that I have to move y. Suppose y is when x is equals to 0, y is equals to 5, then it is not mandatory that when we move x from 0 to 5, then y should change its value, right? That means x and y are totally independent to each other. These are independent things, okay? So these two are not depending. That means this can take value individually by its own law, and this can take value independently of the change of this. That means how these two things can be uh, equal, right? I can change this in any way, right? Like 0 to 5. Then it must also be changed in such a manner that these two things will be same. So that can only be possible if the two things, both of these two things become a same constant, right? Means these two things, these total two things are not actually changing, you can say, right, like that. So 1 by x del to capital X over del x square, let us call it some constant c1, and this thing 1 by y del 2 y over del y square, let us take it as another constant c2. Okay, now what will happen? Now there is only one variable, so I can write it like total differential d2x over dx square, right, equals to c1 into x. Let c1 is equals to k square, some constant, into x. And what about this? Sorry, d2y over dy square. Okay, this becomes minus k square. Why this should be minus k square? Because c1 plus c2, it must be equals to 0, right? If we take this thing here, if we take this thing here, so means if we take this thing right, left hand side, this, then this is what c2, this total thing, and this is what c1. So c1 plus c2 must be equals to 0. That means c1 is equals to actually minus c2. But we will take plus sign here and minus sign here. You can think in another way, that why I am not using here minus and here plus, then also this will satisfy, c1 plus c2 will be 0. Then how can we guarantee that this will be always plus and this will be minus? The reason you will understand later, I will discuss that later. Okay, so the solutions, you can easily understand that this becomes a normal differential equation, right? This is no longer a partial differential equation, now this becomes a ordinary differential equation, ODE. Now the solution of this is very simple. What is the solution? X is equals to a to the power, just the solution, how you can calculate the solution using the d operator, d square minus k square. If we take this left hand side, so this will be equals to 0, or you can replace this d with m square minus k square will be equals to 0, so m will be plus minus k. So the general solution will be a to the power plus kx plus b to the power minus kx, and its solution will be y is equals to, right, y is equals to c sin ky plus d cos ky, because here is a negative sign, so this becomes imaginary, so the solution will be like this. Okay, now what is the total solution v of xy, which was just the product of x and y. So the solution will be a e to the power kx plus b e to the power minus kx. Okay, this into this thing means c sine of do right now. Now you have seen that v, looking at the boundary condition, you can understand that this boundary condition, okay, v is 0 at x tends to infinity. That means v is equals to 0 at x tends to infinity. If you, this is what, this is a oscillatory type of function, right? At y tends to infinity also, this, the nature of the function will be like this. It will not anyhow becomes infinity along the y axis, right? That means this function is oscillatory, we call it oscillatory. This, what is about this at x tends to infinity? This e to the power minus infinity is 0, and e to the power, and whatever this thing, whatever this thing, e to the power plus infinity, right? If we put x tends to infinity, it will be plus infinity, which is tending to infinity. So at x tends to infinity, due to this term, the value of the vxy is becoming to infinity, but which is contradictory to our in boundary conditions number 4, right? So what is making the problem? This term. So just make the constant a 0, then our problem will be solved. Then if we put this thing at x tends to infinity, this will become 0, and this is oscillatory, so the total product will be 0, which is matching with our boundary condition, right? B tends to 0. So a is equals to 0, this is one thing. So what is the form right now? B to the power, and we are taking b inside, okay, inside c and d. I'm taking inside the bracket, okay, for simplicity just, and taking the constant c and d, and another constant c dash or d dash, suppose, or I can make this c dash and d dash and make the new constant, which is the multiplication of b and c dash, to be c. I'm assuming that is c. Why? Now what we can do, now we will use another boundary condition. We will use the boundary condition this, okay. Then what happens? This and this, y equal to 0, this is y. What happens? You can understand that this become d to the power minus kx, this will be 0. Now this is valid, this should be valid for any value of x, right? X can be anything, but this should be 0. So how can it possible? For suppose x equal to 1, if d is not equals to 0, then it is not possible to become the right hand side equals to 0 for any value of x, right? It can only be 0, or it can only match with the left hand side if and only if the d is equals to 0. Then you can say for any value of x, this expression validates. So we get another thing. This is using the boundary condition 1. So d is equals to 0. That means v is becoming what? V is becoming e to the power minus kx c sine ky. Now we will use the boundary condition number 2, which is at y equals to a, v is again 0. So 0 is equals to the v, right here, this. So this will become c e to the power minus kx into sine ka. So how this can be 0? For any value of x, this can only be 0 if this constant, or otherwise this thing is 0, right? Now if you put c to be 0, right, uh, you can easily understand that if c is equals to 0, then this, by this expression you can easily understand that v is 0 always. V is 0 always for c equals to 0, right? If we put c equals to 0, so that cannot be happen. But if we make this to be 0, then you can understand that by this expression, this v can only be 0 at y equals to a. That means at when this sine ky become sine ka, then only this becomes 0. So that can be, right? That can be. So the preferable choice will be to 0 this quantity. This is 0 means what? Sine n pi, where n starts from 1, 2, 3, dot dot dot. Okay, this thing. Then what happens? Then we cannot put here n equals to 0, okay, because if we put a 0, then again this type of things v equal to 0 will always be happen. Okay, now what will be the value of k right now? N pi over a. This is another condition. So what will be the actual solution? V x y is equals to c e to the power minus k, sorry, e to the power minus n pi uh, n pi x over a sine n pi y over a, right? This becomes the solution. Now you can see that the third boundary condition, which was what? Yes, which is v equals to v naught at v equal to v naught. V should be equals to v naught when at x equal to 0. This is valid or not? All the three others are validating this, satisfying this equation, right? But is this satisfying this expression? No, it is not satisfying, right? If we put x equals to 0, then this becomes 1, but y can take any value. So how y can take any value, right? So for different value of y, the v should change. So how this v could be a constant, right? Now this thing, for solving this thing, we'll use another property of the Laplace's equation, and the property is the linearity property. Laplace's equation actually, the form of Laplace's equation is linear, in the sense that what is linear means? Linear means the equation was del square v equals to 0, right? Yes. So if it have several solutions like v1, v2, v3 dot dot dot, then that means del square v1 equals to 0, similarly del square v2 equals to 0, or similarly the others. Then also by the linearity property of Laplace's equation, you can say that all the summation, or you can say the linear combination of all the solutions. That means linear combinations mean this, like this, some constant alpha 1 into the first solution v1 plus alpha 2, some another constant, okay, into v2 plus dot dot dot. This is called the linear combination. So the linear combination of all the things will also satisfy the Laplace's equation. Okay, that means del square v is actually now becomes alpha 1 del square v1 plus alpha 2 del square v2 plus dot dot dot. So what is the benefit of it? Now we can say that, right? Now we'll understand this. Okay, one minute. Previously I have said you that C1 would to take this thing to be positive and this thing to be negative. Now why this I have said this, right? Now just assume if this becomes negative, suppose, and this becomes positive, then what happens? If this thing becomes negative, then you can see that this thing will be now interchanged. What I mean by that, now if this becomes negative, right, this becomes negative, that means this form will not be any longer valid, right? Then the solution of x will be in sinusoidal form, right? If this becomes negative, so the solution of x will be in sinusoidal form, and the solution of y will be in exponential form, right? Then what happens if the solution of x is in sinusoidal form? Then you can understand easily that at the boundary condition is what? At x tends to infinity, or at x equals to 0, the v should be equal to v naught, and at x tends to infinity, the v should be equals to 0. So is this validating? At x tends to infinity without changing y, at x tends to infinity. If x becomes a sinusoidal function, then never it will become 0, right? If this become a sinusoidal function, then as we have discussed, the sinusoidal function never becomes infinity at x tends to infinity. So at x tends to infinity, this v will never be equals to 0. So it is contradictory, totally contradictory to our boundary conditions, right? But if we take it positive, then what happens? Then this becomes an exponential form, the solution of x, and when we put x tends to infinity, then what happens? If we eliminate this term, or if we make a equals to 0, then yes, without changing y, without changing any value of y, if we approach to x tends to infinity, then due to this term e to the power minus infinity, this will become e to the power minus infinity, and that will eventually become 0. That means v will tend to 0 due to approaching to infinity along the x-axis. So that is properly matching with our boundary conditions. So I have, that's why I have taken this positive and this is negative. Okay, now coming to our main thing. So now the solution I can write like this: v of x comma y is equals to now summation, right? This becomes a summation, but n equals to 1 to infinity Cn, okay, for varying c for different value of n, e to the power minus, so for different value of n, actually we are getting different solutions like v1, v2, and we can, if we make a linear combination of that all the solutions, then if we get if we make the linear combination, then that will also be a solution of the then that will also be a solution, right? That means v I can express like a express like this, right? E to the power minus n pi x over a sine n pi y over a. Okay, now let us try to fit this boundary condition. At x tends to 0, what is happening? At x tends to 0, v of 0 comma y, which is nothing but equals to v naught, which should be equals to v naught, right? So this v naught is equals to, this term will goes away at x tends to 0, right? This will become 1. So this will become Cn sine of n pi y divided by a, and there is a summation n equals to 1 to infinity. Now look at this form. This is just similar to the Fourier transform, Fourier series. If you have studied the Fourier series in your mathematical course, then you will understand easily. This is exactly like the expansion of any function in Fourier coefficients, like, right? Where Cn, you can easily understand that Cn is what? Cn will become here, like in the Fourier expansion we have discussed, we know that if the function v naught here, right, it is the function v naught, it's a function of y, and in the Fourier series we have we know that in the Fourier series we discuss like this. If there is a function like f of x, and if it validates, or if it follows the Dirichlet's conditions, okay, that is meant, then even if there is certain amount of or finite amount of discontinuities, and there is also there is 4 actually conditions in this Dirichlet condition. Okay, I am not going to discuss that, but if this function f of x, which is nothing but equals to v naught of y here, follows the Dirichlet's conditions, and in that conditions, in that 4 conditions, there is a condition that if it, even if this function have finite number of discontinuities, then also this function can be expressed as an expansion of a even function and an odd function. That means a sine and cosine functions with proper uh, values of the coefficients, which is the actual um, thing of Fourier series, right? That means it can be expressed as summation an sub constant an cos nx or n pi x over a plus summation this type of thing. So here actually this thing is happening, right, where Cn will be equals to 2 over a integration 0 to a v naught. How this becomes, this is called Fourier coefficients. You can easily understand that this is the actual expression, but what is the problem here becomes, what is the value of Cn? We don't know. We don't know what is the value of Cn. The problem that was happening before that, the boundary condition that is at x tends to 0, this is not this was not this thing was not equals to v naught, right? But that thing is now uh, overcome due to this Fourier series. Now becomes a series, and any Fourier series we can express any function like here v naught of y at x tends to 0. This becomes v naught of y. This should be become v naught of y, this expression, right? But now this becomes a Fourier series. This is a Fourier series. Now as this becomes a Fourier series, and we can express any function which uh, which just maintains or obeys the Dirichlet's condition. We are assuming that v naught of y is as obeying the Dirichlet's condition. Then any function like here, for example, v naught of y can be expressed as a Fourier series, and that Fourier series is nothing but this. So this is actually mathematically valid. So yes, the boundary condition, that is this boundary condition at x tends to 0, v should be equals to v naught of y. Yes, this is validating here, this is obeying here. So our problem is solved, but we are not aware of what will be the value of Cn. No, that is very much easy. If you know Fourier series, you can easily understand that how this thing comes. But for simplicity, I am making it clear. I want to make it clear. Okay, what we have to do, if we multiply both sides with sine, now sine n pi y over a into sine, suppose m pi y over a. If we integrate this over 0 to a dy, then this will take value 0 when m is not equals to n. You can by your hand calculate these things, okay? And when m is equals to n, then this become, then that means actually what, sine square n pi y over a 0 to a, the value of this integral becomes a over 2. This is the rule. That means is I am writing the right hand side. So n equals to 1 to infinity Cn sine n pi y over a into sine of m pi y over a, right? And then if we integrate this thing, if we make an integration over 0 to a dy, then you can easily understand that this will only be a finite number, or this will only be a by 2 only when m is equals to n, and otherwise it will become 0. So we are just considering with only this condition, m equals to n. That means Cn sine square n pi y over a dy integration 0 to a summation n equals to 1 to infinity, and this is the right hand side, and the left hand side will become 0 to a integration v naught of y into sine of, actually sine of m pi y over a, but now imposing this condition sine of n pi y over a dy. And what we have discussed, that this will become a by 2, this is the value of this integration. So this will become a by 2 Cn, right? This will collapse to this condition, right? Okay, there will be no summation because only when if you take it, only when n equals to, it can take any value, right? This will expand, right? N equals to will be 1, then 2, but for any value m is fixed, right? M is fixed, but this will change if we expand this what we call it, expand this summation, then n will take different values, but for different values, whenever only when m will be equals to n, m will match with n, then only this integral will be a finite number, and otherwise it will become 0. So all the other terms will become 0, and only when, like this, only when n equals to m, then only that term will exist, and that term is nothing but this. So there will be no summation here. Okay, so this a, now a by 2 into cn, which is equals to this. So if we take this here in this side, then what becomes, cn will become 2 over a 0 to a v naught of y sine n pi y over a dy. Now if you calculate these things, okay, 2 over a will be, and v naught will be taken outside, and if you calculate 0 to infinity, 0 to a sine of n pi y over a dy, and that will, and multiply with that this thing, then you will end up with this thing. For even value of n, that will vanish, and for only odd value of n, that will become this value. Take this value. So our ultimate solution will become cn, right? The value of cn becomes now this. Cn means 4 v naught over pi. N will be taken inside the summation, right? 1 over n e to the power minus n pi x over a into sine n pi y over a, right? So this is the ultimate solution of that problem. This is the solution of this problem. Now I think that you have understood all the concepts, okay, how these things becomes okay, and if you have benefited from this video, then subscribe this channel and share this video with your friends. And in the upcoming videos I will also discuss another type of problems of electrostatics, like the Laplace equation solution in spherical polar coordinates, which is quite difficult, or quite you have to learn more things, like the Legendre polynomials. Okay, so in the upcoming videos I will make that things also. So take care of yourself. Thanks for watching.